Welcome back to DeepVisus, where vision meets depth. In today's episode, we're diving into Chapter 12 of Stephen Grossberg's insightful book, Conscious Mind Resonant Brain, titled From Seeing and Reaching to Hearing and Speaking. This chapter explores how our brains process not only what we see and how we move, but also how we hear and speak, revealing fascinating parallels and deep connections between these sensory and motor systems. So here's the question we're after in this episode. How does the brain unify the seemingly different tasks of seeing, moving, hearing, and speaking into coherent, stable, and conscious experiences? And what fundamental neural principles underlie this remarkable integration? To start, Grossberg introduces the concept of cortical processing streams, two key pathways in the brain for both vision and audition. For vision, we have the classic what stream that identifies objects and the where/how stream that handles spatial location and action. Interestingly, the auditory system mirrors this setup with a ventral pathway for sound to meaning and a dorsal pathway for sound to action. This homologous organization hints at shared neural strategies across senses. A central idea in development is what Grossberg calls circular reactions. Babies spontaneously move their limbs or babble sounds, then use the sensory feedback from these actions to form associative maps, linking sensation and motor commands. This learning loop is key not only for mastering eye-hand coordination, but also for developing speech. From there, Grossberg presents elegant computational models of motor control, starting with the vector integration to endpoint (VET) model, which explains how the brain calculates smooth reaching movements by continuously comparing the current position to a target position, generating movement commands that vary in speed, direction, and muscle coordination. This model shows how the brain handles changes on the fly, such as switching targets mid-movement, which is something we do effortlessly every day. Building on that, the Vector Associative Map, VM, model adds a layer of learning calibration. It shows how babbling movements during development help the brain fine-tune these sensor-motor maps to maintain accuracy as our bodies grow and change. What's really fascinating is how these motor control principles extend to speech through the direct and diva models. These models describe how we learn to produce speech sounds in a motor equivalent way, meaning we can use different muscles or articulators to produce the same sound, and how speech develops from babbling to refined volitional control. Co-articulation, the blending of sounds and natural speech, emerges naturally from these neural controls. Grossberg then explores auditory scene analysis, the brain's ability to separate overlapping sounds, like picking out one voice in a noisy room. Here, the ARTSD area model explains how spectral pitch and timbre resonances allow us to track and consciously perceive distinct auditory streams. It models the auditory continuity illusion, where the brain fills in sounds occluded by noise, demonstrating how perception can actually lag behind incoming sounds to create stable, coherent experiences. A critical developmental step is speaker normalization. How babies learn to map varied speaker voices into stable, speaker-independent representations. This process enables language learning and understanding across different speakers and voices. The NormNet model proposes that speaker normalization may have evolved as a specialization of auditory streaming circuits, emphasizing the brain's efficient reuse of mechanisms. Grossberg also highlights strip maps and asymmetric competition as general brain design principles. These mechanisms provide extra space in cortical maps to organize multiple features, whether for visual processing, auditory streaming, speaker normalization, or even numerical cognition. Speaking of numbers, the chapter delves into how parietal cortex circuits underpin our ability to estimate and represent numerical quantities, building from shared evolutionary foundations with spatial and motion processing. The SPAN and E-spine models explain how place value number systems, like those we use in everyday counting, may emerge from interactions between what and where streams, bridging sensory representations with language. To bring this all together, the brain unifies vision, movement, hearing, and speech through shared computational principles, adaptive resonance, circular reactions, strip maps, and competitive dynamics that enable stable learning, flexible control, and conscious experience. These mechanisms create robust, motor-equivalent behaviors and perceptual invariance, allowing us to interact fluidly with a complex, dynamic world. So, what's the answer to our initial question? The brain integrates these sensory and motor functions by leveraging homologous processing streams and resonance-based learning, using developmental circular reactions and dynamic competitive maps to build stable, adaptable representations that support perception, action, and communication. That wraps up this episode of DeepVisus, where vision meets depth. In our next episode, we'll explore how these foundational principles extend to memory, attention, and higher cognition, diving even deeper into the neural symphony that orchestrates conscious experience. Stay curious, and see you next time.